SwayamPrabha. Digital India. Educated India.
Welcome back. We will continue our discussion of multi-phase modeling of sprays. Towards the end of last class, we had sort of arrived at a taxonomy of multi-phase models to see a possible way by which you could, based on the physics of your given problem, choose an appropriate model. Whether you should be using a Lagrangian model, or whether you should be using an Eulerian multi-phase or a mixture model, or the exact model that we discussed as our choice number 1. Okay. So, we will start from there and look at the mathematics of some of these models and see what underlies the mathematics. Okay. So, we said based on the particle relaxation time and the mean free path, these are the two parameters we defined based on which you could choose between the different models, and in the gray area of course you have to, there is some room for engineering judgment. Apart from that, of course, we said the exact model would be applicable in all these situations. So, let us look at the governing equations for the mixture model. If you recall, the mixture model is essentially a single phased version of a multi-phase model. That is, in reality we have drops laden in air, that is our spray, but we believe due to certain physical laws that the spray seems to obey, that we are able to make a simplification and look at a third equivalent fluid which is a mixture, and we will only write our balance laws for the mixture. We are not at this level going to be concerned about individual droplets or air as being separate. We are only going to write a balance law for the mixture. So, the first balance law is the conservation of mass. That you will see here. But before I go to the conservation of mass, we need to be clear about our definition of alpha. Alpha is called the volume fraction, and this is the fraction of a given space, a given infinitesimal spatial region that is occupied by either phase 1 or by alpha I is the volume fraction of the ith phase in the mixture, where a certain volume of a given infinitesimal volume is occupied by the ith phase, and that fraction is given as alpha I. So, remember, this is a field property, that is, it is a function of x, y, z and time in general, which means that at every point I am looking at a tiny infinitesimal volume surrounding that point, and I envision alpha I as being the fraction of that infinitesimal volume that is occupied by the ith phase. So, we sort of touched upon this, that the idea of our infinitesimal volume now is not our old calculus mathematical infinitesimal volume, but it is a volume small enough in comparison to the rate of variation of alpha I, but big enough in comparison to individual drop sizes. So, we cannot be talking about an infinitesimal volume that is on the order of the drop size. We are looking at an infinitesimal volume that is bigger than the drop size. So, I can talk of a smudged out volume fraction. So, the first constraint that we have from that is this fact that the sum of all volume fractions has to equal 1. So, this is essentially what you might call occupancy of space. I cannot have empty space. In a continuum formulation, there is no such thing as emptiness. So, I have essentially all the space occupied by either air or my drop phase. We are not talking drops, we are talking drop phase. That is our, so if I was to only talk of a two phase problem, in the two phase case m would be equal to 2 and then I can define alpha 1 and alpha 2 and alpha 1 plus alpha 2 has to equal 1. Now, based on the local alpha I can define a mixture density. And alpha and rho I is what we will call the material density. So, that is the actual physical density of the liquid I am spraying and actual physical density of air, the material. Those are my rho i's. Rho m is the local mixture density, that is the density of the constituent, the mixture phase that is made up of these two materials. So, now I have my mixture density, and so we will come back and define our conservation of mass, which looks very similar to our single phase conservation of mass equation that we usually have accompanying our Navier-Stokes equations, that the partial derivative of alpha I rho m with respect to time plus the gradient of alpha I rho m V m is equal to 0. V m is the mixture velocity field. This mixture velocity field is basically based upon the idea that locally at that point both the air and the drop phase are moving with the same velocity V m. This is a velocity field, of course. So, it could be a function in general of x, y, z and time, and alpha I rho m V m, gradient of that quantity plus the rate of change with respect to time of alpha I rho m is equal to 0. Now, notice how I still have the subscript I, which means that this is an equation that we write for each of the two phases. So, alpha I rho m for each I you have a conservation of mass equation. So, just to be clear about that fact, I will say this is a conservation of mass equation for phase I. Now, if I take the simple two phase formulation and I take an equation just like this with I being equal to 0 and I being equal to 1 and I being equal to 2 and add them up, let us see what we find. If I take summation over all I, what I find is that I have rho m summation alpha I plus gradient of rho m V m summation alpha I is equal to 0. We already know summation alpha I is equal to 1. So, I can write this as gradient of the mixture density plus derivative of mixture density with respect to time plus the divergence of rho m v m is equal to 0. In fact, this is exactly the mass conservation equation for a compressible fluid, which means all we are saying in the mixture model is that this effective fluid is a compressible fluid and the constituents of the compressible fluid are these alphas, and this rho m being equal to alpha I rho I summation is like my equation of state. Remember, we need an equation of state for a compressible fluid to close the set of equations. So, essentially this rho m being equal to summation alpha I rho I is like my equation of state. It is not yet completely formulated as the equation of state, because I need another property that says rho I itself is a constant. So, if I know that rho I itself is constant, so if I treat my air and my liquid as individually being incompressible in the material sense, rho m being equal to alpha 1 rho 1 plus alpha 2 rho 2 is an equation of state that relates the density of this mixture to a property, a field variable called alpha 1. Remember, I do really only alpha 1 is an independent variable, alpha 2 has to be 1 minus alpha 1 in the two phase description. So, rho m is equal to alpha 1, let us write this out and just be clear about it. So, rho m is equal to alpha 1 rho 1 plus 1 minus alpha 1 rho 2. If I let this be accompanied by rho 1 equal to constant and rho 2 so if I say rho 1 and rho 2 are individually constants, this is saying both the individual phases are themselves incompressible, then rho m equals alpha 1 rho 1 plus 1 minus alpha 1 rho 2 is the mixture density, and this is essentially sufficient to be called an equation of state, because I am relating the mixture density to a field property called alpha. Okay. And I have an evolution. So, in as far as this mixture conservation equation is concerned, this mixture conservation equation is the compressible the mixture is a compressible fluid, and this is a conservation equation for that compressible fluid. The property of that mixture is related to another field variable called alpha 1, for which this is my transport equation, this is my conservation equation for that alpha 1. Okay. So, this is now, as far as conservation of mass is concerned, we have defined what the fluid is looking like. Now, in the momentum sense, this is essentially my conservation of momentum equation. Okay, the partial derivative with respect, so this is again familiar. There is two parts to this. I have now a mixture pressure, and simplest of multiphase models. So, if I take the constitutive relationships and say my Pm is independent of the simplest of constitutive relationships, could be that Pm is independent of all alpha and gradients. So, it is just like my hydrostatic pressure field in the air phase, okay. Or I could relate tau m to the simplest forms would be relating Pm to only alphas and relating tau m's to only gradient of Vm, just like a Newtonian fluid would behave. Okay. So, let us move on and we will look at the next level of complexity, which is my Eulerian multiphase models. The Eulerian multiphase model again starts by writing a conservation of mass equation for each of the So, this is for the I equal to 0 phase. There is a particular reason I have written this in this form, but really it does not matter. I could have let this I go from 0 to m and it would not make any difference. Okay. So, now I have this conservation of mass for each of the phases constituting the mixture, but the difference now is that we are going to write a separate conservation of momentum equation for each of the phases. What have we done in this process? Let us look at our list of dependent variables. We have alpha, if I simply take m equal to 1 here, m equal to 1 would mean a 2 phase flow, because I equal to 0 is one phase and I equal to 1 is another phase. So, I write an equation like the top two here for my I equal to 0 and an equation like this for I equal to 1. And I have alpha 0 is one of my unknowns, rho 0 is just the material density of the fluid, V 0 is a velocity field that is unknown for the phase 0. Likewise, I have alpha 1 V 1, I have P 0 P 1, tau 0 tau 1, these are my unknowns. I can come up with a relationship, or we will have to come up with a relationship between P 0 tau 0 and alpha 1 alpha 0, the gradients of the velocities, that is what we called our constitutive relationship. We also know that alpha 0 plus alpha 1 has to equal 1, that is our occupancy of space relationship. Now, in addition, so we have essentially created, as opposed to the mixture model, we now have one more new velocity field here, which is my V 1, which is new. So, we have in 3 dimensions, we have 3 velocity components and alpha for each of the 2 phases. So, this is, I have 8 unknowns at every point in space apart from the 2 pressures, So, once I relate the pressures to some other field variables, I have 2 pressures, 6 velocity components in all and 2 volume fractions. That is my complete list of unknown variables, as opposed to the mixture formulation where we had 2 volume fractions, 3 velocity components and 1 pressure. So, we have essentially added 4 more unknowns to the list. The problem is not just the addition of 4 more unknowns, it is the numerical complexity and the solution complexity that comes with it that and that poses some convergence challenges for this kind of a model formulation. The simplest assumption made, so now look at the pressures for a moment. We are able to postulate an individual pressure field in each of the 2 phases in this kind of a formulation, but they are not really completely independent of each other, and so the list of unknowns becomes smaller through algebraic relationships that exist between these kinds of other variables, like for example alpha 0 plus alpha 1 has to equal 1. So through relationships between these individual field variables, the total number of independent unknowns comes down slightly, but we have not yet touched upon this term here that did not exist in the previous formulation. So, now that I have 2 phases, let us just take I equal to 0 and I equal to 1, and the 2 phases are moving with different velocities, they become sources and sinks of momentum to each other. So, I can have interphase momentum transfer that now becomes important. Notice the form of this term K0I is like a drag coefficient, and that coefficient multiplied by the differential velocity, the relative velocity between the 2 phases, is a simple constitutive model for a force, a drag force that exists between the 2. So, drag is the simplest of these interphase momentum transfer terms. Now, again if I assume I equal to 1, there is a K01 which is dependent on the relative velocity between the 2 phases, that takes on a positive sign in one equation and a negative sign in the other. Okay, this is basically saying the force acting on one phase is equal and opposite to the force acting on the other. And if I take all the equations, all the balance laws for each of the different phases and add them up, that gives me the, even in this formulation I can derive a mixture level balance law, but that would have the individual velocity components remnant in it. So, I could still define sort of a velocity of the center of mass of the mixture. I know now that the 0th phase I equal to 0 is moving with one velocity v 0, I equal to 1 is moving with a different velocity v 1, but based on the relative volume fractions and mixture densities, we can define what is called a barocentric velocity of the mixture. Okay, and we can write a formulation for the barocentric velocity of the mixture, and in that formulation these interface drag terms vanish. So, interface drag cannot affect the barocentric velocity of the mixture because it is a force internal to the whole mixture, but it does affect the individual phasic movement, velocity fields in the individual phases. So, let us for a moment look at this shear stress terms tau 0 and tau I specifically. What is tau I? Tau I is basically the shear stress field that exists in the drop phase. So, if I take a collection of drops with no air in between, if I try to put a hook on one of the drops and drag it, does this drag other drops with it? That is the basic definition of shearing, right. So, if I pull one drop with me or a small group of drops, what does it do to the other drops? If there is no effect on the other drops, that means the effective viscosity of this collection of drops is 0. There is no shear stress that can be sustained in this mix, in that collection of drops. So, if I now take this collection of, how do I now find the viscosity of this collection of drops? One would have to do, or the effective viscosity of this collection of drops, one would have to do fully resolved simulations to look at the effect of collisions between drops, which is basically responsible for this effective viscosity, and derive from sort of an inverse from a regression these kinds of constitutive relationships. Okay, and this is, like I said, an active area of research in itself that would be worth pursuing to complete, to bring these model formulations up to some level of applicability where they are more realistic for dense sprays. So, why do I say dense sprays? If I look at rarefied sprays and do this same thought experiment of putting a hook on a small group of drops and dragging them, because they are a very high Knudsen number collection of drops, the effective viscosity of something like that would be basically 0. Whereas, if you are in the dense spray region where collisions are more frequent, then if I try to do this thought experiment in the dense spray region, you can imagine that the effective viscosity of this mixture would be non-zero. And so, this shear stress term sustains itself in the dense spray region, while it goes to nearly 0 in the rarefied region. Okay. I want to pause here for a moment and show you one possible way by which you could look at modeling. What use are these kinds of models in a real spray? What use are these Eulerian models in a real spray? So, one of the areas of applicability of these Eulerian multiphase models in sprays, especially when you have breakup and coalescence, is to look at population balance modeling. So, we will look at what population balance modeling is for a moment. Let us say I have a little box with lots of different drops. Okay. And just for the sake of convenience, I am going to divide these drops into different bins. So, I have let us say drops spanning from some d min to some d max. I am going to divide this into different bins. So, this is my ith bin, this is I plus 1th bin, this is I plus 2. So, if I want to look at how to model breakup, let us say. So, initially all the drops are of this large size and there is some process that is causing these drops to break up. So, if I take the number of drops in the ith bin and write and that is some Ni, why would Ni change? Ni changes because of two reasons. Because drops in the ith bin are breaking up. So, if gamma I, which is often called the breakage frequency, okay. So, if the ith drops are breaking up if the drops in the ith bin are breaking up at some rate. So, gamma I is a rate of breakup of drops, then gamma I times Ni with a negative sign is the rate of breakup of drops, and that is essentially with a negative sign taking drops out of the ith bin. The other possibility is that I have some drop in the I plus pth bin, okay, breaking up and putting some mass, putting some number of drops in the ith bin. So, when a drop that is larger than the ith size class breaks up, it puts drops in the ith bin. So, I have some other jth size class breaking up at the same rate gamma j n j, and a fraction of that gamma j n j, which is given by this n I j, coming into the ith bin, and I could have this go over all the drops from I to m. Really speaking, it should be I plus 1. I cannot have the ith bin breaking up to give drops in the ith bin. So, at best I could have the I plus 1th bin breaking up to put drops in the ith bin, or I could have the I plus 2th bin breaking up, putting drops in the ith bin, etc. So, this n I j is a fraction of drops that end up in the ith bin from a breakage event in the jth bin. So, this n I j is a fraction of drops that end up in the ith bin originating from a breakage event in the jth bin. Some drop in the jth bin broke up, and it breaks up into lots of fragments. It could break up into 2 equal halves, it could break up into one big drop and one tiny fragment flying off, it could do lots of different things. And this breakup event now puts some fraction of those drops originating from the jth bin into the ith bin. Okay. So, this is a balance of the number of drops in the ith bin, which due to breakup. So, when I have some breakup process causing these drops to break up, some physical process, we do not know, that physical process has to obey something like this. Okay. Now, this is called a phenomenological model. Notice how I have not yet brought in any physics of what is causing this breakup. The physics is essentially hidden in these constitutive coefficients gamma I and n I j. This is my opportunity to bring in the physics. Say for example, I might believe through a physical process that a larger drop is likely to break up more frequently than a smaller drop. So, for example, if I believe that there is a smallest size drop that just does not break up, then I might say that gamma 1, which is the breakup frequency of the smallest size class, is 0, and I might write a relationship between gamma I and d I, the size of the drop, or I might write a relationship between gamma I and some other property that is imparting this energy for breakup to the drops, and Nij is our phenomenology of how a given size of drops breaks up. So, if a drop breaks up, is it likely to break up into 2 equal halves, in which case my Nij, so if it is exactly breaking up into 2 equal halves, then say for example N24 would be 1 and all other Ni4 where I is not equal to 2 is 0. So, if for the case of j equal to 4, so I am just looking at drops originating from breakup happening in the 4th bin, and if let us say for a moment that all the diameters are spaced equally in an arithmetic progression, then a drop breaking up in the fourth bin only puts drops in the second bin, because it is breaking up into two equal halves, and it cannot put drops in the third bin or the first bin. A drop breaking up in the 100th bin puts drops only in the 50th bin and in no other bins. So, this is a phenomenology that is based on some physical understanding of that particular breakup process. So, the population balance model that we wrote, this part is only a framework. It is a phenomenological framework. The physics comes in the form of these gamma i's and nij's, and over the course of the last, let us say, decade or so, the various models have been developed for both gamma I and nij to accurately capture the physics of a given physical problem. Say for example, we have a multiphase reactor bubble column, where you have bubbles of some size coming in at the bottom of the column and they may break up and leave, and we want to look at the phenomenology of the breakup of these bubbles, because that is important to creation of surface area. The creation of surface area is important to mass transfer. So, if I look at the mass transfer process, and if I want to model that mass transfer process, I need to model the evolution of the size distribution of, let us say, drops or bubbles or whatever the case may be. Okay, so, what we are going to do now is look at how we can take our regular Eulerian multiphase model governing equations and include these population balance terms. So, essentially we looked at drag as being the only coupling between these two. In fact, if I take a two phase formulation of this, there is only two coupling mechanisms between the individual phases as it is apparent in this case. One is through drag and the other is through occupancy of volume. So, alpha 0 plus alpha 1 has to equal 1. If I now look at what happens if I include population balance, I have these drag terms, but I also have additional coupling in the form of these population balance source terms. So, think of what this means. If I have the drops in a box, the left hand side of the drops in a box population balance was just dni dt, okay, which is the rate of change of the number of drops in the ith bin as a function of time. When I now have a flow field superimposed over these drops, I have to write the material derivative of that flowing field. So, in the Eulerian formulation, where I have these drops coming into a control volume and leaving while these breakup processes are happening, the first thing that you see is that the left hand side is now of the form of the material derivative, where alpha I is the volume fraction of the ith phase. And if you look at what you see on the right hand side of these equations, you see this alpha I by xi, xi is essentially the size of drops in the ith bin. It is actually, let us be even more clear, it is not just any size, it is the actual volume of a drop in the ith bin. So, volume of a drop in the ith bin. So, alpha I is the total volume fraction, alpha I by xi gives me the number fraction of drops in a given point that reside in the ith bin. So, you see that the rest of this equation looks very similar to the population balance form, except I have this gamma I ni, what looks like ni, and gamma j nj times some nij, which is a fraction of the drops that come over into the ith bin. And because I am looking at a multi-phase formulation where I say each of the size classes is also allowed to move with its own velocity field. If we go to that level of generalization of the flow field, then drops breaking up in one phase resulting in showing up in a smaller size class are also bringing in momentum with them, because total momentum over the entire mixture has to be conserved. The breakup of drops from a larger size class putting drops into a smaller size class is completely internal to the whole air plus drop mixture. So, whatever momentum exchange processes that happen are supposed to be equal and opposite. So, that is the reason for these two terms that you see in the red ellipses, where any momentum leaving the jth phase accompanying the mass transfer from the jth phase to the ith phase ends up in the ith phase. Likewise, any momentum leaving the ith phase due to breakup of drops in the ith phase leaves the ith phase. Okay. Again, these are only phenomenological. So, this is some breakup process, this is some process, it is like a balance law that tells me mass coming into the ith phase and mass leaving the ith phase, mass and number of drops are sort of related. So, how do I let this mass come in and go is where the physics of the problem comes in. So, for example, in a general flow situation like this, the actual breakup of drops is due to a relative velocity between the air and the drop phase. So, we could relate the gammas to some kind of a relative velocity in the drop phase, and when you do that, essentially this is a model of secondary atomization that follows your primary atomization process. So, you have some primary atomization that produces a distribution of drops, and from there on you could look at studying the secondary processes using a phenomenological model like this. This is where you can take multi-phase models and apply it to atomizing sprays. Without this atomizing part, this red is essentially the atomization part of the multi-phase formulation. Without the atomization part, these are my governing equations. These are my governing equations, where if I have the balance laws and the appropriate constitutive relationships, and I know the size of the particulate phase, because this drag coefficient is going to require some information of the size of my dispersed phase drops. So, if I know the size of the dispersed phase drops, I have this equations complete that I can look at transport of drops in the spray. I cannot include how the process of these drops breaking up without the help of something like a population balance model. This completes our discussion of multi-phase models and mixture model, Eulerian model, but I just want to leave you with a sort of a thought. We went through this process of asking ourselves some physics based questions and finding and arriving at a model choice that is appropriate. In reality though, most of our models are neither here nor there, or they involve both. So, I will just take a simple hourglass that is flowing sand. If you look at the Knudsen number, which is the distance travelled by a given particle between two collisions. If I look at the Knudsen number in this region versus the Knudsen number in this region, they are vastly different. This is a case where if you imagine these sand particles are all jiggling, and these jiggling sand particles are going to collide very frequently. So, this part is ripe for our kind of a continuum model. This part after you have gone past the constriction is essentially where individual particles are moving with no knowledge of their neighboring particles. They are all falling in the same gravitational field with about the same terminal velocity, if they have reached a terminal velocity. But the mean free path, which is the distance between collisions, has gone up significantly during this process. So, if I ask the question, what model is appropriate for this? This is actually a very close representation of our real spray. We have a very dense spray region where we require a continuum model, where we can, I mean, because of the frequency of collisions, you either require a model to handle the frequencies of collisions in the individual particle, in a discrete particle model, or you go to a continuum. And on the other count, when you have reached into the rarefied region, you require something that defaults to where individual particles are moving with no knowledge of other particles around. This is an area that is an active, this is an area that is research wise very active. To patch rarefied spray models like Lagrangian particle tracking is a very good choice for rarefied spray models, but you require some kind of an Eulerian model in the discrete, in the dense spray region. Patching these two together is what real life research these days looks like. Okay. We will continue our discussion in the next class.